Welcome back to the Foundry by Forge College. So, in our previous lesson, we covered the introduction to parallel transaction processing, right? Well, today's explainer, scheduling and conflict detection, builds directly on that. As part of our Mechanics of Parallel Execution module, we're zooming way in. We're going to map out the exact blueprint for safely scheduling thousands of transactions all at once. This is really where theory meets the metal. Let's dive in. Here's our agenda for today. We'll be hitting conflict detection, dependency graphs, a worked example, parallel batches, and factory rules, before wrapping up with a quick recap and next steps. Basically, we're going to treat the C-level execution environment like a highly optimized factory assembly line. So the big question we need to answer is right here on the screen. How do we process thousands of tasks simultaneously without any data collisions? Just think about it for a second. If you've ever tried to assemble a car while someone else is simultaneously trying to paint that exact same part, you know it's a disaster. You end up with a useless Franken car. An unmanaged factory floor is just a recipe for absolute chaos. We absolutely need a way to bring order to that chaos. All right, section 1. Conflict detection, the primitive. Let's step onto our factory floor and look at the fundamental rule that stops our workers from fighting over the exact same equipment. Our most basic building block here is the read-write set comparison. I know, it sounds a bit complex, but it really just asks a simple question. Do worker A and worker B need to use the exact same tool, or in our case, the exact same account, at the exact same moment? We're literally just looking at the footprint of each instruction sequence to map out exactly what it intends to read and exactly what it intends to modify or write. Notice how we categorize these interactions. Look, two workers reading the same blueprint. A read-read scenario, that is perfectly fine. They can share. But if one reads while the other edits, what we call read after write or write after read, well, then we've got an unsafe overlap. And if both try to overwrite the document simultaneously in a write-write conflict, oh man, that's a major collision, and it absolutely requires strict deterministic ordering to resolve safely. Moving on to section 2, dependency graphs, and how we build them. Once we actually spot these dangerous overlaps, we have to do something about them, right? We convert them into strict rules. You can kind of think of the dependency graph as the ultimate factory flowchart. The vertices are our instruction sequences, and the edges, which are drawn as directed arrows, encode our execution constraints. These arrows mathematically force one task to completely finish before the next one can even begin. It takes all that subjective messiness of the factory floor and turns it into pure objective order. But hey, watch out for this. Beware the cycles. If task A is waiting on task B, but task B is simultaneously waiting on task A, boom, we hit a cycle. It's basically an infinite loop of bureaucracy, and the entire assembly line just grinds to a halt. To fix this, we have to break these cycles using deterministic tiebreakers, like, say, relying on the original input order, to just force a resolution. I really love this quote. Dependency edges are the canonical representation of conflicts. By converting raw overlaps into these rigid edges, we stop worrying about individual accounts entirely. Instead, we start working with a pure mathematical model of time. We aren't looking at accounts anymore. We're looking at an undeniable timeline of exactly what must happen first. All right, section 3, the worked example. Let's put this blueprint to work. Let's put on our hard hats and walk through a concrete example with 5 tasks. Here's our raw data. We have 5 transactions labeled T1 through T5, showing exactly which accounts each transaction needs to read and write. For instance, T1 reads accounts A and B, but it writes to C. Take a quick second to look at where the letters overlap between these rows. Those overlaps? Yeah, those are our potential collisions. So to turn this raw data into a humming assembly line, our scheduler runs through 4 strict mechanical steps. First up, pairwise comparison. Second, we assemble the graph. Third, we detect 0 in-degree nodes. And fourth, we use levelization to group them into batches. Let's see how that looks. Looking at step 1 in action. Because T4 modifies account A before T1 needs to read account A, we have a clear write after read scenario on our hands if we aren't careful. So we have to draw an arrow, a dependency edge, pointing from T4 directly to T1. T4 must happen first, period. And we do this exact same thing for every single overlap in that table we just looked at. Which brings us to section 4, creating parallel batches, or grouping our tasks. Once all those arrows are drawn between our 5 tasks, we can start grouping the independent ones together. We scan our newly built graph for tasks with 0 in degree. Honestly, this is just a fancy way of describing the lucky workers who aren't waiting on anyone else to finish. They have 0 incoming arrows. In our specific example, if you mapped out all the edges, you'd find that T3 and T4 have 0 in degree. They are completely unblocked and ready to go. And this brilliantly illustrates the magic of scheduling. Because T3 and T4 are unblocked, they become batch 1 and execute at the exact same time. Once batch 1 finishes, it removes its constraints and unlocks T1 for batch 2. When T1 finishes, its outgoing arrows vanish, which then unlocks T2 and T5 for our final, highly optimized batch 3. Boom! We just safely processed 5 transactions in 3 parallel waves.
Now for Section 5, Factory Rules and Optimization. Let's tune the floor.
The basic blueprint is great, but as we often teach in our advanced programs at Forge College, you have choices in how you run your floor. You could choose levelization, which is what we just did. It's simple, reliable, layer-by-layer execution. Or you can dial it up and use greedy packing. This actively crams as many tasks as safely possible into a single batch. Greedy packing gives you maximum throughput, for sure, but it requires much heavier computational checks to make sure you aren't breaking any rules along the way. To keep the whole system from jamming up, regardless of which method you choose, we have to enforce strict heuristics. We use deterministic tiebreakers to ensure our schedules are reproducible. We use hotspot avoidance to actively prevent contention where way too many tasks want the exact same account, kind of like a crazy popular NFT drop. And we use batch size caps to limit latency and memory use, so the scheduler itself doesn't just crash the entire factory. So the crucial takeaway here is this ominous mathematical formula on screen. Big O of n squared times f. You've got to remember the engineering cost of all this checking. As the number of transactions goes up, the math required to check every single pair against every other pair absolutely skyrockets. This means keeping your dependency graph sparse, having your transactions touch as few shared accounts as possible, is absolutely critical for speed. Finally, Section 6, Recap and Next Steps. Let's wrap this up. Let's wrap up this factory blueprint and see where these beautifully organized batches go next in our C-level execution journey. Here's your quick recap. First, we compare read and write sets pairwise. Then, we assemble directed dependency graphs. Next, we use deterministic tiebreakers to resolve any pesky cycles. And finally, we emit 0 in-degree batches. The massive takeaway here is that static scheduling completely transforms dangerous, chaotic read/write overlaps into safe, dynamic, parallel execution. It's a total game changer. But, the job isn't totally over. These static, perfectly ordered batches are exactly what feeds into our next topic. Next time, we're going to cover handling the messy, dynamic reality of runtime conflicts, live resource locking, and what actually happens when the factory floor encounters a real-time glitch. Which leaves me with one final, provocative question for you. What happens when the perfect static blueprint meets the chaotic, dynamic reality of a live network? Think on that. If you're ready to master this, answer that question, and build your own high-throughput assembly line, make sure to visit forge.college to explore this subject in depth, dive into our community, and check out other advanced Web3 topics. Thanks for joining me for this explainer, and I'll see you in the next one.